So this is the one, yeah. Starting with this, the solubility, hydration, and conductivity of ions of group 1 metals. So, देखिए, many times you read books, you read only the text part. You leave this kind of the tables and the graphs that is present, the schematic diagram. So you try to just look at it and think what it tries to convey. तो आपको पता चलेगा कि बहुत सारी चीज़ें जो लिखी नहीं गई हैं वो भी समझ में आ रही हैं. So of course there are some questions that, so what does this table conveys? You can look at it. It is the table that tells you about ionic mobilities and hydration. So look at this, lithium plus, so we are moving down the group, size of cation, ionic radius 0.76, 1.02, like this. It is increasing down the group. Okay, and when you talk of ionic mobility, or when they are in a very dilute solution, such that the two cations are not able to interact with between themselves, so that is infinite dilution, what we mean. You make it okay. So what happens is that there is a water molecule. I told you that when you dissolve Na+, जब आपको बोर्ड पे मैंने ड्रॉ करके दिखाया था कि Na+Cl- जब डिजॉल्व होता है तो Na+ gets surrounded by a large number of water molecules. In a similar fashion, you can think of this number will be different, lithium plus, Na plus, K plus. As you go down, the size of cation increases, the electric field, the charge by size, if you calculate the charge to size ratio, charge by size, that gradually, because the size increases, charge remains constant, so this factor also decreases down the group. ठीक है, down the group decreases. So what is going to happen? The interaction with water will weaken. So मतलब क्या होगा कि आप लिथियम से सीजियम प्लस की तरफ जाएंगे तो उतना strongly, so lithium plus will be having a very strong field. It is small cation, it will be surrounded by large number of water molecules. Na plus will have a weaker electric field. In that sense, it will attract water molecules much less, slightly less as compared to this. So if you look at the number of water molecules associated with it, look at this. Lithium plus is having approximately, on an average, 25 number of water molecules associated with it. Na plus, कोई knock, who is this? एक minute. I saw someone trying to enter the group class. Anyway, हाँ, तो मैं पॉइंट जो बताने की कोशिश कर रहा हूँ वो ध्यान से देखिए इसमें कि लिथियम प्लस smaller size, so so the charge, same amount of charge but in a smaller volume. Na plus 1 unit of charge but in a larger volume, and this is the thing. So electric field becomes more and more intense in case of lithium plus. H2O, which is basically behaves, you can see the interaction of H2O and lithium as lithium plus as ion dipole interaction. I told you that one Na plus will get surrounded by Na plus, or lithium plus can get surrounded by water molecules in this fashion. So it is ion dipole interaction that we are talking about. Okay, large number of, so we are, so ड्राइंग जब हम बनाते हैं तब तो जितना दिखा पाएंगे उतना ही बना पाएंगे ना, लेकिन एक्चुअल में जो ये नंबर होता है ये काफ़ी ज़्यादा होता है संख्या. ठीक है, so this number is actually for lithium plus 25.3, Na plus 16, and gradually as the size of cation increases, this hydration number decreases. So cesium plus is hardly, they are surrounded by or roughly 10 water molecules as an average, whereas lithium plus, the first cation of the group from the top, is 25. the number is 25, huge. So each of, जैसा मैंने आपको बताया कि ये जब ion dipole interaction होगा, this will leave, there will be, it is attractive in nature, a large amount of energy is released, and that is reflected over here. See this, delta H is negative. So down the group, this is negative, means 542 kilojoules of energy is released when 1 mole of lithium plus dissolves in water, right? So hydration number and delta H, you can see it is highest in this. Also, because there are 25 water molecules surrounding one lithium plus, if you look at the radius of the hydrated ion, so this is a hydrated ion, this is what we call as hydrated. So hydrated ion will become larger than the corresponding ion. So see the change, 0.76 to 3.4, 1.02 to 2.76, like this. So if you look at the hydrated ion, this one is the largest. Look at the hydrated ion, because there are 25 number of water molecules surrounding it, 3.4, whereas it is 2.28 for this. So you can see कि बहुत बड़ा अंतर है. अगर प्योर आयनिक रेडियस आप देखते हैं आइसोलेटेड एटम में, तो ये ऐसा है ट्रेंड, 0.76 से 1.76, सो लाइक 1.67, जो कि 75.75, तो लगभग डबल से थोड़ा ज़्यादा हो रहा है. लेकिन यहाँ पे 3.4 उल्टा ट्रेंड है. सबसे ज़्यादा लिथियम प्लस का है साइज. अगर हाइड्रेटेड वाटर मॉलिक्यूल जो टाइटली बाउंड है उसके साथ, उनको हम लेते हैं, क्योंकि वो दे आर स्ट्रांगली, these are water molecules which are surrounding that cation, and वो जहाँ जहाँ जाएगा उसके साथ साथ मूव करेगा. सो ये हाइड्रेशन शेल की तरह एक काम करता है. और you have this is what we call as hydration shell. So we will talk about this more in these few slides. And so what is the effect overall? You see the mobility, it is surprising, you will find it surprising that ionic mobility, मतलब जो आयन का मूव करने का, वाटर में आप पैरेलल प्लेट इलेक्ट्रोड अप्लाई करें और उसमें बैटरी से कनेक्ट करें, the circuit will be completed when, if it has ions, it will move from positive plate to negative plate. Ions will start moving and you will have conduction will happen. So that from that data we are able to calculate the ionic mobility, and you will be surprised to see that ionic mobility is maximum. So the conductivity also, conductivity of the solution is maximum for this cesium plus, not for lithium plus. So that is because it is that each of these ions is hydrated. It has, that is, it is surrounded by a large number of water molecules, and that water molecules which are tightly bound to it, they make look like, appears like, it appears like a shell is encapsulating these ions, and this ion plus the hydration shell moves together throughout. So उसका साइज तो बढ़ गया, 25 वाटर मॉलिक्यूल जुड़े हुए हैं इस लिथियम प्लस के साथ. इसका साइज 3.4 एंगस्ट्रॉम है. calculate. So it will move, if you are looking at this size, largest and smallest in terms of the ion with the hydration shell, so the movement will be much slower for lithium plus, and cesium plus will move much faster, and so the conduction will be more. Ionic conductivity increases for cesium plus. So it is contrary to the initial view that you might be having कि lithium plus तो छोटा है, ये ज़्यादा आसानी से कंडक्ट करेगा, इधर से उधर मूव करेगा जब इलेक्ट्रिक फील्ड अप्लाई करेंगे. सॉल्यूशन में उल्टा होता है, क्योंकि हाइड्रेशन शेल बड़ा है लिथियम प्लस के लिए, उसका साइज सबसे ज़्यादा बड़ा. Okay, so this is something that we have to keep in mind while discussing these points. So we have 0.76, 3.4 is the hydrated radius, whereas so increase, so it is almost 75 से ये 35, ये बहुत ज़्यादा बड़ा हो गया, आप देख रहे हैं ना, इसका इंक्रीज बहुत कम है, द इंक्रीज इन साइज is less, so the effect is also accordingly there. एक minute, I can see someone is knocking here. Anchal, okay. ओके सो ये एक हाँ पैटर्न है जो इंटरेस्टिंग पैटर्न है जो हम लोग देख रहे हैं यहाँ पे, ये भी एक्सपेक्टेड है। सो जितना ज़्यादा वाटर मॉलिक्यूल्स एसोसिएटेड होगा, आयन डाइपोल इंटरेक्शन समेशन ऑफ दोज फोर्सेस will turn out to be each of these is attractive in nature, summation of this, so in each of these interaction energy is released, and so delta H is also larger with a negative sign, energy released negative sign, okay. हाँ, और क्या दिख रहा है इसमें, सो ये सब सारी चीज़ें आपको दिख रही हैं, नोट किया पॉइंट, इसका चेंज हाइड्रेशन के बाद, इसका चेंज देखिए, ह्यूज चेंज, कितने टाइम्स बढ़ गया, डबल ट्रिपल, 5 टाइम्स, ऑलमोस्ट 5 टाइम्स, 4 to 5 टाइम्स चेंज हो रहा है लिथियम प्लस के लिए, हाइड्रेटेड आयन से आयनिक, आइसोलेटेड आयन से हाइड्रेटेड आयन के बीच में, और यहाँ पे 1.67 से 2.28, नॉट मच चेंज. So all the salts of group 1 dissolve in water and they conduct electricity. Lithium plus ions are small, and although we expect them to conduct better, yes, क्या हुआ, क्या लिख रहे हैं, कोई मैसेज कर रहा है, it appears like no. So ये इंटरेस्टिंग पैटर्न है ट्रांसफरेंस, हाँ, okay. So all contrary to expectation, it is the cesium which is the best shows conduction, highly conducting. So that is due to, so it is so that we can explain when we analyze the actual situation in the water, in the aqueous solution, that is each of these ions are surrounded by water molecules and the hydration shell is larger for lithium plus, and so its movement is slow, it moves along with hydration shell. So ionic mobility or conductivity measurements shows that cesium, this is the order of thing, cesium plus is most maximum conductivity and lithium plus the least. So this is the anomaly is explained based on the hydrated, when we consider the hydration. Lithium plus is small, heavily hydrated, and hence moves slowly. Cesium plus is least hydrated and moves faster. So this is this picture conveys that same idea, how what happens here. So here you can see ionic radius and then this. So the blue circle that you are seeing is the ionic radius, pure ion, and this white thing that you are seeing, it is the overall hydrated ion. So gradually left to right the blue dots are increasing, but the white shell, the hydration shell is shrinking, right? The hydration shell is shrinking, becoming smaller and smaller. So this trend is important. It is the hydrated radius which determines the conductivity of the solution. Similarly, when you think of the second group, magnesium, calcium, strontium, barium, again the trend is similar. You can see 0.7 ionic radius for magnesium 2 plus, which on hydration, it is magnesium 2 plus is having 2 unit of charges, double that of lithium. So the interaction with water molecules is going to be much stronger, and so you can see here the number from starting from point 0.7, there's a much larger number of water molecules which surround this magnesium Mg2 plus ion, and so its solution shell is even bigger, 4.28. उसके बाद फिर सॉरी हाँ 4.12 इस तरह, सो इसमें थोड़ा सा इस तरह से वेरिएशन आ रहा है, तो आप देख सकते हैं. सो सॉल्वेशन शेल, जो हाइड्रेशन शेल है, वो छोटा होता जा रहा है, और when you are moving down the group, number of water molecules is largest for the smallest ion and gradually decreases. So now we look at this hydrogen shell in a much more detailed. So what happens is the first few water molecules are actually covalently linked. So how does that happen? We can just look at this. Some of the water molecules touch the metal ion and form a complex that, you know, they are vacant orbitals in the lithium plus, where this lone pair of water can be donate its electrons. So that kind of situation arises here that we can imagine. So this is the lithium atom, you can see 2s1. Now lithium plus, this electron is gone, you are left with only 2 electrons in the 1s. And now, so if we can think of sp3 hybridization, then 4 orbitals of equivalent energy, same energy, can be prepared, and in each of these orbitals 4 electron pairs coming from water donate the electrons. So a covalent bond, coordinate bond is formed. Covalent coordinate bond is formed. See, a coordinate bond is essentially similar to what we have discussed in covalent bonding. The only difference is that the pair of electrons, the 2 electrons come from one species. So here water contributes the 2 electrons, and the orbital containing the 2 electrons overlaps with the vacant orbital of lithium sp3, right? And that is how, so it is also a covalent bond in which both the electrons have been contributed by water in one lithium plus. So there are four water molecules which are associated, which are strongly bound to the lithium plus, and this is how it explains. First, this is the primary shell, and primary shell involves covalent linking, the coordinate through coordinate covalent bond. 4 water molecules are linked, okay, and through the lone pair of oxygen, okay, and with 4 electrons the valence, so it will appear to be tetrahedral because of, if you consider the lone electron pair repulsion. Okay, so now if we consider, so rest of the water molecules that we have considered about 25. We were in previous slide, we have seen that there are actual 25 water molecules associated with one lithium plus. मतलब एक लिथियम प्लस के लिए 25 है, हमने 4 के लिए तो लिखा कि ये कोवलेंटली लिंक कर सकता है, करता है, बाकी के क्या, बाकी सबका इलेक्ट्रोस्टैटिक, प्योरली इलेक्ट्रोस्टैटिक इंटरेक्शन होगा, ठीक है. यहाँ पे ये कोवलेंट लिंकिंग हो गया, एक कोऑर्डिनेट बॉन्ड जिसमें दोनों इलेक्ट्रॉन एक ही स्पीशीज की तरफ से आते हैं, एक ही एटम डोनेट कर रहा होता है, देता है, जो शेयर्ड पेयर बनता है उसमें, ठीक है. सो अब इसी तरह से अगर हम सीजियम प्लस का देखें, तो सीजियम और प्लस और रुबिडियम प्लस, इसमें आपके पास यू हैव ऑप्शन, they can undergo, so there's here d orbitals are available in the outermost shell. In case of lithium, it was the outermost shell was having n is equal to 2, which have only 2s and 2p, but rest of the ions will have in that group will have availability of 3d d orbitals as well, And so when we are talking about, say, a simple example, we can take K plus. So this is the potassium, electronic stature of potassium in the ground state. You have 4s1, uh, and then K plus electronic structure. So here the electron is gone, and now you can have this for so you have here potassium, and then when this is, you can, this K plus have vacant orbitals. D orbitals are also low lying in terms of energy, so hybridization can happen when the in this case D2sp3 hybridization can happen, and 6 orbitals are made available for donation of electron pair by 6 water molecules. So each of these cesium plus and rubidium plus ions or K plus ion have, which have d orbitals available in the outermost shell, they can undergo this kind of uh, hybridization and can covalently link and form a covalent coordinate bond with 6 water molecules. This is the primary shell, and the secondary layer develops in which it is purely ion dipole interactions, which is held together by just simple consideration of charges on the metal ion and the dipole. So these are much weaker interactions as compared to the previous one, the primary shell. So primary layer, secondary layer. So two kinds of layer. When we are looking at an hydrated water molecule, hydrated cation, then these are two types of interaction that water can have. One is covalent linking through coordinate bond formation, what lone pairs are donated, and in the second one it is purely ion dipole interactions, and this is more in number. As we can see, in case of lithium plus, only 4 are binding covalent, forming covalent bond, rest 21 in the secondary layer. So the strength of such force is inversely proportional to the distance, so that if the size of metal cation increases, then this secondary layer interaction will decrease, and this is the reason why you have this kind of thing. Secondary hydration decreases from lithium to cesium, and therefore we have lithium plus being the most heavily hydrated. The size of hydrated ions is an yeah, it is very important biologically through movement through cell walls, and uh, so if you need to have sodium potassium pump, that is most suitable. The size is in that sense. It also explains the behavior on cation exchange columns, where lithium plus attached less strongly and hence eluted first. And there are also things like yeah. So that was the description of solubility and the conductivity of ions in solution. Now uh, in the same group we are going to discuss the enthalpy of formation for group 1 halides. If you look at this is a graph which shows delta H formation on the y-axis, and on the left x-axis you have the atomic number lithium, that is you have atom lithium and sodium potassium. So down the group you have increase in, so all the group elements lithium potassium, they are arranged in the order of increasing atomic number, increasing proton number, and then you get this kind of graph. What does this show? This is a negative, all are with negative sign. So this is the energy released when during the formation of this mx, metal halides bond. So what you see here, the trend is something very interesting here. For the halides, Cl, bromide, iodides, chloride, bromide, iodide. As you move from lithium, sodium, potassium for iodide, there is almost very linear increase. Sorry, my hand just got slipped. Okay, so it is almost a linear kind of trend, just like a line. So minus 270, 280, 328. So the amount of energy released when enthalpy of formation, this goes on increasing as you move from left to right, keeping this thing constant. Bromide ion, see, minus 315, 360, then it is going on like this. So how do you explain this? Okay, so जैसे जैसे आप लेफ्ट डाउन द ग्रुप मूव कर रहे हैं, कीपिंग द हेलाइड फिक्स्ड, सो आयोडाइड को पकड़िए और मूव कीजिए लिथियम प्लस, लिथियम आयोडाइड, सोडियम आयोडाइड, पोटेशियम आयोडाइड, तो एक इंक्रीजिंग ट्रेंड आता है ऐसा, ठीक है, 270 से 347 तक। उसी तरह से फिर आप ब्रोमाइड को पकड़िए, आप देख सकते हैं कि ये इंक्रीजिंग ऑर्डर में है। लेकिन क्लोराइड में भी वैसा ही ट्रेंड है, लेकिन सबसे ज़्यादा हैरानी की बात है कि जब फ्लोराइड को देखा जाता है तो उल्टा हो जाता है, द ट्रेंड गेट्स रिवर्स्ड, trend is reversed here. When we take the fluorides of all group 1 elements, we find that trend is reversed, that it goes on decreasing as the size of cation increases. Why is this so? ऐसा क्यों होता है कि फ्लोराइड वाले में ट्रेंड उल्टा हो जाता है, घटने लगता है अमाउंट एंथैल्पी ऑफ फॉर्मेशन, minus 616 for lithium, and which finally for cesium it becomes less, minus 554. This is very surprising again. So ये सब जो अनयूजुअल सरप्राइजिंग जो रिजल्ट्स है, मैं उन्हीं सब चीज़ों पे फोकस कर रहा हूँ आपको, जो थोड़ा मुश्किल है समझना, नॉर्मली बुक्स में उतना अच्छे से नहीं दिया होता है, तो वही चीज़ पॉइंट्स में पहले पिक कर रहा हूँ. So what is happening here? So so what we see here, most of the halides, sorry, कहाँ गया slide? Solvation shell, okay. So what we see here, most of the halides form a 6 to 6 coordinate, जैसे NaCl में बनता है वैसा ही बनता है, लेकिन सीजियम के जितने सॉल्ट्स हैं इसमें 8:8 कोऑर्डिनेशन होगा, ठीक है, सीजियम के जितने भी सॉल्ट्स हैं उसमें 8:8 कोऑर्डिनेशन होगा, और ये यहाँ पे आप देख रहे हैं ऐसे. और क्या इंपॉर्टेंट चीज़ है, द एंथैल्पीज ऑफ फॉर्मेशन of all the halides are large and negative. Yes, this is a general observation, all are negative and large as compared to any other salt, and it becomes less negative from fluoride to iodide for each element, less negative from fluoride to iodide. So if you are, ये दूसरा तरीका है देखने का कि अगर हम एक ही मेटल को फिक्स रखें, सपोज वी कीप टेक लिथियम, and lithium combines with iodide, bromide, chloride, fluoride. So fluoride is having minus 600, and this gradually decreases for minus 400 for chloride, minus 351 for bromide, like that, and minus 270 for lithium iodide. So keeping the cation fixed, if you vary the anion, there is a decrease, and same trend continues here for cesium plus, cesium iodide, cesium fluoride. If you compare so there is gradual decrease in the delta HF, the formation enthalpy. So as you move from fluoride to iodide. Okay, and we also see that yeah, the enthalpies of formation become less negative for the fluorides on descending down the group and more negative for the chloride, bromide and iodide. Chloride, bromide, iodide. Hmm. So that we have seen minus 616 to minus 554, it is becoming less negative, and here from anything iodide, bromide, it is becoming more negative as you move down the group. So we have already seen this trend, what is written. So the answer lies in the when you construct a Born-Haber cycle for each of these, you can get the answer why this is happening. The trend is like this. So this is a Born-Haber cycle, generalized one. Metal, metal gaseous, then this ionization enthalpy, dissociation of uh, yeah, uh, halogen. Okay, so hmm. So so what we have, so Born-Haber cycle is similar to what we have did in the class. Okay, nothing is unusual thing here, and you can see the arrows. You started with this reaction MHAI. So this is the halide. Sorry, HAL halide. HAL is written here. This is halide ion halide. So this is your formation enthalpy, which can be represented as a sum of delta S sublimation enthalpy, ionization enthalpy, dissociation energy, electron gain enthalpy for the halide halogen, and then the lattice energy. This is lattice energy, right? Lattice energy, or in more precisely expressed as enthalpy, lattice enthalpy. So why, how do we explain the trend that is there? So enthalpy of formation, as we had discussed previously, must be delta HF. This one should be equal to the sum of all these things that happen while moving through the cycle. So this is the sum of all these forces: sublimation, ionization, dissociation, and electron gain enthalpy, and this lattice energy. Now what happens here? You can see a few things here. Delta H dissociation for the different halides are given. Sorry, different halogen molecules are given. Dissociation energy. Electron gain enthalpy is given here, minus 328, less than chlorine, minus 349, which is maximum. And then you have a trend like this. Now if you sum these two things together, dissociation energy, electron gain enthalpy, overall trend is minus 249 to 20. So amount of energy released, sorry, the sum of the two is that overall it is negative, because electron gain enthalpy is much more as compared to the dissociation energy. So first thing is that, and then we also find that fluorine has maximum value of these two things taken together, and then it decreases amount of energy released, considering only these two aspects. So what we have seen here, first two terms, sublimation, ionization, if you keep the metal ion fixed, for given metal ion these two terms are constant. For given metal ion this will remain constant. The only variable will be dissociation of the dissociation enthalpy of the halogen and the electron gain enthalpy. So what happens here? So these are three terms that will, and these two terms actually they will keep varying from vary from fluoride to iodide. This is the thing that we are talking about. What will vary? This will vary. Dissociation energy and electron gain enthalpy. आयोडीन को डिसोसिएट करना है, I2 से I बनाना है, वो ज़्यादा आसान होगा. अगर फ्लोरीन अगर F2 को दो फ्लोरीन एटम्स में कन्वर्ट करना है तो वो ज़्यादा मुश्किल होगा. So accordingly we can see the values turn out to be like this, and we can see that through the table this value gradually decreases as we move from chloride to iodide, fluorine to iodide in fact. If you look at the lattice enthalpy, so if the radius of cation and anion increases, any one of them, the lattice energy will decrease. So it is a function of proportional to the sum of r plus r minus. It's lattice energy. Okay, radius of cation, radius of anion. As the radius increases from fluorine to iodine, the lattice enthalpy becomes lattice enthalpy. We have this here. So as radius of an ion increases, lattice enthalpy will decrease, right? Because r plus r minus has increased, so lattice delta HF becomes less negative. Now, if we consider the formation of so these two things, group I halides, then dissociation energy. So if we fix, let's say fluoride only, if you fix the fluorine and then move down the group from lithium plus lithium, sodium, potassium, then these two things are fixed, and the only variable will be sublimation and ionization, which is also given in the table. So lattice enthalpy also decreases as the radius of cation increases down a group. Radius of cation becomes, if the cation becomes smaller, lattice enthalpy also decreases, because of the increasing size, the electrostatic interactions becomes weaker. So the determining factor, what are the factors that control the overall thing? If you look, we can look at it this way. The enthalpy of formation depends on the relative difference between these values, that is sublimation enthalpy, ionization enthalpy minus lattice energy, lattice enthalpy. So overall trend will become what will happen for chloride, bromides, iodized? What happens? This term delta H sublimation plus delta H ionization, this is the change much bigger change, right? But if we look at the and so if this change is bigger than the change in delta H lattice, so as compared to lattice energy, the less change in this lattice energy. Okay, so because of that, overall thing will be that it will become, formation enthalpies will become more negative down the group. Delta H, lattice enthalpy is changing less. Sublimation energy is decreasing. So as you are moving down the group, sublimation energy is changing, ionization energy is changing. If you fix the, and then so let's say iodide. For iodide, what is constant? The other in electron gain enthalpy, the dissociation energy is constant. The variation, so for all iodides, the variation from lithium to cesium will come out based on this consideration of these things. So down the group, sublimation energy decreases, ionization energy also decreases, lattice enthalpy decreases down the group because the cation is becoming larger, but the decrease in this value is much more than the decrease in enthalpy. So I should put it another way. Let me put it this way. What happens here, that for all of them, like we are fixing this thing, iodides. Let's analyze iodides and say cesium, lithium to cesium, lithium iodide, sodium iodide, potassium iodide, rubidium, cesium. So if we look at this, the variation in this pattern, the pattern will be due to, not due to the electron gain enthalpy, not due to electron affinity or dissociation energy, but the factors that depend on the metal ions. So size of the metal ions control the interactions. So you will have this will, so the variable is the delta H sublimation plus delta H ionization. Okay, this decreases down the group. Other variable is the lattice energy. Second variable is the lattice energy, delta enthalpy, delta HL also decreases down the group because the size of cation is increasing in size. But the important thing to note is that the decrease in delta H sublimation plus delta H ionization, this term, if you compare the decrease in this and with decrease in delta HL, then this decrease, what I am saying is that this is much greater, and so decrease in sublimation energy is much more than this thing. So overall things turn out to be negative because the positive, these were, what were these were energy released, sorry, energy required. ये सब एनर्जी रिक्वायर्ड था जो कि कम हो गया, इसमें डिक्रीज ज़्यादा हो रहा है. और जो एंथैल्पी है जो कि नेगेटिव टर्म है, it was a positive term and this was a negative term, energy released था. सो ये जो है उतना चेंज नहीं हुआ, इसमें उतना डिक्रीज नहीं हुआ, तो ओवरऑल क्या होगा, चीज़ें नेगेटिव ही रहेंगी, नेगेटिव ज़्यादा होंगी. ठीक है, और यही चीज़ हमें देखने को मिलता है यहाँ पे कि ओवरऑल जो ग्राफ है वो लेस नेगेटिव से मोर नेगेटिव हो जाता है. क्योंकि ब्रोमाइड, आयोडाइड और क्लोराइड के लिए द चेंज, द डिक्रीज इन enthalpy of sublimation and the enthalpy of ionization is much greater as compared to the decrease in lattice enthalpy. ठीक है, मैग्नीट्यूड की बात कर रहे हैं, जो मैग्नीट्यूड है वो उसमें ऐसा चेंज आता है। सो इसलिए ओवरऑल चीज़ें और नेगेटिव हो जाती है। ठीक है, लेकिन फ्लोराइड के केस में क्या है कि फ्लोरीन का साइज बहुत छोटा है और उसके केस में it is the properties are mostly dominated by the size of cation only, और बहुत ज़्यादा फर्क नहीं पड़ता है जब हम सॉरी if we go for this या हाँ ये बता रहा था ना आपको, हाँ इसको मिटाना होगा, discard all these things what I had written. So this was the trend that we have observed, uh, which has been observed for this cations. So for all chloride, bromide, iodides, this change is greater than the variation in delta HL. So this becomes more negative down the group. But in case of fluorides, the ionic radius of fluorine is much smaller, and the delta H sublimation, delta H ionization. So in this particular case, this decrease in the lattice enthalpy will be much more. So when we have fluorides, what is happening? So when we are talking about lithium fluoride and sodium fluoride, cesium fluoride, what happens in this case? Fluorine much smaller in size. So it is, so overall when you sum it up, so here also lattice energy decreases, you also have a decrease in the delta H sublimation plus delta H ionization, these things also decreases, but the decrease in delta HL sublimation plus delta H ionization, this one, the decrease is so so what will happen? The decrease in sublimation plus delta H ionization, this decrease is smaller as compared to the decrease in delta HL, lattice enthalpy, and so it becomes overall less negative, or it is moving towards positive. Okay. So in this particular case it will become less negative down the group. So because cation plus anion R plus R minus जो है ना वो बहुत ज़्यादा affected नहीं हो रहा है, जो lattice enthalpy है it remains largely very less affected by the change in the size of cation. Okay, so this one is और फिर solubility of ये जो cations आयनिक सॉलिड्स हमने डिस्कस किया है, ये डिसॉल्व करता है, जब आप वाटर में डालते हैं तो ये डिसॉल्व कर जाता है, So you have mx crystal, and when you so डिसोल्यूशन के लिए भी एक बॉन्ड हेबर टाइप साइकिल हम बना सकते हैं. So consider mx it happening in steps. So you have defined lattice energy as the difference of one when one mole of, so it is the reverse of that thing. When you have already have the crystal, you give the amount equivalent to the lattice energy, and it will dissociate into corresponding ions. Now these ions, when they are dissolved in water, they get surrounded by a certain number of water. So m plus hydrated, x minus hydrated, and a large amount of energy is released uh, due to ion dipole interactions. Ion dipole interaction. So already discussed in class and just a few whiles back also. So if the hydration energy is more than if the hydration energy is greater as seen here than the lattice energy, which is, then the process is spontaneous. It will happen easily. Lattice energy. So this is a negative term. Energy is released. Here the lattice energy, the way it has been treated, it is a positive term. Energy is required, and so if the hydration energy is more than the lattice energy, it will readily dissolve. It is okay. If the situation is vice versa, lattice energy is more than the hydration energy, the substance may not dissolve. It will not. It is difficult to dissolve something. Which is okay. So something becomes, so कोई चीज soluble है, insoluble है, वो इस साइकिल के बेसिस पे आप एक्सप्लेन कर सकते हैं. So substance to dissolve, the hydration energy must be greater than the required to break the lattice, which is okay. So if hydration energy is more than this, it will always dissolve, but if it is less, then it will not dissolve. So if the solid is hydration energy less, then the solid is insoluble. So this kind of situation you can see here in the hydration enthalpy of the group I halides. So you can clearly see for lattice energy for MF, MCl, MBr, all of them. So for lithium maximum, you can see lattice energy, and then it decreases down the group magnitude clearly. Chloride, same trend, like that. So free energy of hydration delta G star maximum for lithium, and then decreases down the group. So the reason why this solubility of most group 1 metal decreases at descending the group is the lattice energy only changes slightly, but the free energy of hydration changes more. You can see लैटिस एनर्जी में उतना चेंज नहीं है. यहाँ पे 500 था फ्री एनर्जी चेंज, और यहाँ पे 275, ऑलमोस्ट हाफ हो गया. सॉरी, हाफ से थोड़ा ज़्यादा है, लेकिन हाँ तभी काफ़ी कम हो गया है. बट इफ यू आर लुकिंग एट दिस, इट इज़ स्टिल नॉट मच चेंजिंग. 845 to 644, 800 to 600. तो उस तरह का शार्प चेंज लैटिस एनर्जी में उतना चेंज नहीं आ रहा है जितना कि फ्री एनर्जी में चेंज आ रहा है. एंड सो द ट्रेंड, so you can clearly see that yes, when we say KCl is less soluble than NaCl, this is for the same reason. Okay, KCl plus versus NaCl. NaCl free energy of enthalpy is more for NaCl as compared to this. So lattice energy is this 67 kilojoules, and yet the difference in delta G hydration for Na plus is 76 kilojoules, and that's why KCl is less soluble than NaCl, right? So okay, so I stop here and I will take a few more classes on Sunday or Monday. I will tell you the next class. Then we will finish. Okay. So thank you.